Okay, welcome everyone to the session number 3. So this is our lecture number. Lecture number 3, which is going to be mainly focused on linked lists. Okay. So the problem in general with lists is that we want to store a list of some items. Now, typically that is done, as we saw, a very common way is using an array, right? So one obvious way you saw, we stored the list of integers in an array. And you did also your lab assignment on the topic of array. Can you think of some disadvantages that you might have encountered? So disadvantages of using an array.
So the size of an array is has to be predefined and can't be changed.
You can
using classes.
have dynamic allocation, right? So if you have dynamic allocation, so when you say predefined, can you be a little more clear on what do you mean by that?
The memory for the actual array elements is has to be initialized.
That's right. So what does that mean effectively? That the arrays, that's a good point. So arrays have a fixed length, right? Whether it is statically allocated or dynamically allocated. I don't know why my handwriting is really going clumsy today. So arrays have a fixed length, right? That's what you're mentioning here. Any other disadvantages you saw as a part of your lab assignment?
It can be really expensive if you dynamically allocate and need to copy over the array once they start getting really large.
Basically, what you're saying is if we need to reallocate for any reason, then it can become really expensive, right?
Yeah.
Right. So in other words, when do we need to reallocate typically?
When the array is full. Like all of the integer slots in the array are full.
Yeah, you're thinking more in terms of the adjustable array, right now. I'm just thinking about something like this, as simple as this, right? So you have 50 elements, right? And you have some number 2, 5, 6, 7, something, 10, right? Let's say you have everything kind of really not fully covering the 50 elements yet. Let's say you have covered until 30 up till this point, and then you have more space to go. So you may have still space. Do you still see some trouble?
Yeah, if you want to add something, you have to copy over everything and like make sure the order is right, basically.
Yeah, so add something where typically that's a problem for array.
So in the middle, for example, somewhere in the middle.
Exactly. So if you have to insert, so if I have to insert somewhere, that's a trouble for arrays. Then you need to make an adjustment by making a copy. So insert an item either at the beginning or middle somewhere is a problem. And so typically for insertion, therefore, this is going to take time proportional to the length of the array, right? So this is going to take time proportional to the length of the array. Now, as far as time is concerned, we will introduce more formally, but at this point, you can just appreciate that this is going to take some time. Just 1 second, okay? Just 1 second. Just give me 1 minute, okay?
Matt, can I ask a random question?
Sure thing.
It's about grading. How can we see? I'm not saying that the final grades should be ready yet for the labs and whatnot, but how do we see those when those are done?
The what? Sorry.
The final grades for labs and homework.
Right. So you should be able to see it on Gradescope. The Lab 0 grade should have been released. Yeah. So if you go on Gradescope, you should see the results, and it should show you the auto graded results immediately after submitting, and then
Right. Yeah.
yeah, you see it. Good.
Yeah.
All right. So let's see. So I hope this point is clear that this is going to take time proportional to the length of the array because as you mentioned that in the worst case, you may have to copy the entire array one place forward in order to create a room for insertion. Do you want me to show this more specifically, or I can just assume that you understand exactly how the shift is going to happen? Anybody not clear on this point? Then I can write in terms of the code how that looks like.
Could you just explain the proportional part specifically?
All right.
I know the code makes sense, but
You would like to see a code?
I think I understand the code, but I don't know if I specifically understand
Okay.
proportions.
Let me just take an example. Okay. All right. So suppose you have filled up 0, 1, 2, 5, 8, something. So there are total 6 elements here, right? And overall, you can see, let's say at this moment, the last index is here, okay? And this is what your array is pointing to. So now suppose you want to insert at this point 8. So what do you have to do? You have to keep shifting each of these forward, right? So after you have shifted this one, then this becomes free. And then you insert 8 here. So now in the worst case, you can see the amount of shift that you have to make is the length of the whole array. That makes
Understood. Thank you.
okay. Very good. Any other question on this point? Because this is the key motivation that is going to drive our introduction to the linked list. Okay. Just move up a little bit to create space. Okay. So linked list is considered to be a recursive data structure. It is the most fundamental data structure that you're going to learn in this course, and at the same time, very powerful one as well. Oftentimes, linked list is also considered to be self-referential for the reasons you're going to see shortly. So what is a linked list? A linked list is made up of what is called nodes. So you can think of node meaning just like a box, you know. The question is that once you have a box, what can you do? That box can have an item. So if the item is an integer, then you have an item in the integer inside the box. So the first thing is that each node in a linked list has two things fundamentally. I mean, it can have more things, but minimally you have two things. And what are the things you have? An item, and this item can be of any kind. Any kind meaning any type. It can be made up of your built-in types, or it can be made up of abstract types that you might be creating by introducing new classes. And each node, in addition to containing an item, it also has a pointer. But pointer to what? Pointer to another node. So next node. So a pointer to the next node. So next node. So clearly when you are thinking about having a pointer to the next node, so next node where? Next node in the list. And that's how you are linking up. So therefore, because of this arrangement, the linked list is drawn typically like this. So you have a pointer to the next node, and the node looks like this. So it contains some item, 7, 6. And then this is again pointer to the next node, 3, let's say. Again pointer to the next node. So how further can I go like this? What happens? Can anybody think of what can happen? Can I just keep going like this?
You point to a null pointer again.
Right. So in order to end the linked list, it has to point to nothing. And likewise, the linked list you can see has a starting point. So something has to point to the start, and that is oftentimes referred to as a head pointer, which points to the beginning. Okay. So with this understanding, now let's try to see how it would look like in terms of the implementation. So you can create a class. So what class would be defined then? If you have to create a class that represents this, what should we call the class?
Node.
Right. So we can call as a singly linked list node. So SLL stands here for singly linked list. So in this case, it is called singly linked list because there is only single link that is involved with respect to a given node. Okay. So let's just put a singly linked list prefix here, and then we will see what else can we build out of this. So right now, without any loss of generality, let's just identify the type of the item as integer. So we can say M because it's a member within the class item. And what is the other thing that is there inside the node? There are two things, right? So one is the item, and what is the next? What is the next item in the list? It's the next node pointer, right? So, and what is the type of that? So this is M node, sorry, M, call it M next. What is the type of this?
Of SSL node, I think.
So SLL node.
The pointer.
So you have to use a pointer here. Can you tell me why we have to use a pointer here? Could we not use a pointer here? Based on what you have learned so far? Why do we need a pointer here?
It's like, if you don't have the pointer, aren't you just instantiating an object of the type of the class SSL node? You're not actually pointing to the next node, right?
Yeah, which is fine. You wanted to instantiate, right? Because every item is pointing to another item, right? So it's almost like you are saying that the node is containing another its next node. That's going to work perfectly fine, right? My question is that why do we need this pointer?
Oh yeah, well my answer was like, if you don't have the pointer, then you're just like, you're not pointing to the next thing. You're just like instantiating like an object, right?
Okay, when is the instantiation going to happen?
Runtime.
Sure, but it's at the construction time, right? When you are constructing, you may construct by pointing out that this is the node that you are copying, or like without a pointer, essentially either you are copying something or you are constructing at the time when you're calling the constructor for the SLL node. What is it that the pointer gives us? You could potentially even think of having a reference if you want to avoid a copy.
Without a pointer, it'd be like a huge pain if you wanted to move data members around. Like if you wanted to like reverse the list or add something, it would seems like it'd be a big pain.
It will be just copying. There will be copy constructor invoked here and there. But there is something fundamentally not going to be possible if we are not using a pointer here.
You need that so you have the null pointer to mark the end of the list.
Exactly. You need to end the list somehow. So therefore, because we need to have the possibility of being a null pointer, therefore this has to be a pointer. You do not have a choice. All right, just to keep our life simple, either we can make it a struct, because we don't want to right now write all these access functions, the public access function, because when we make it a struct, this is by default public. Okay, but when we are writing program, we'll never expose any data members in a public manner. So let's make that a rule. You should always have an interface going on whenever you need to access a content of a data member. Okay, but right now, because we are in learning mode, we'll just simplify our life a little bit. Okay, so now if I have to construct a linked list, let's say what I wrote down here, 7, then 6, 3, let's just say we want to construct this. So what should we do? We can say SLL node star, let's say N1 equal to, what should we say? New SLL node, right? So this is going to allocate the data for N1, right? And then what do we have to say? We have to set, so N1 dot M item, you have to say this is equal to 7. And then N2, sorry, SLL node star N2 equal to new SLL node, and then you have to say N2 dot M item equal to 6, and then SLL node star N3 equal to new SLL node, and then we can say N3. Okay, I'm making mistake all throughout. There should be arrow here. So N3 M item equal to 3. And then finally, what should we be doing? What is missing here? We have, so far what we have done is that we allocated the nodes, and we have, so far what we have done is that we have allocated the node. So you have this 7. We've allocated the node, put in 6 here, allocated the node, put in 3 here. What is remaining?
Setting up the head and the pointers.
Yeah, first of all, kind of linking them up is missing right now, right? So what should we be saying? We should say N. So now, right now we have N1. This is the N1. This is N2. This is N3. This is literally pointing to this node. N2 is pointing to this node. N3 is pointing to this node. So we can say N1 should point, the next, so M next. So this is the M next, should point to N2. So when we do that, then this relationship gets built. Then N2 M next equal to N3. As soon as we write this, then what we did is we build this next connection. And then finally, we want to do N3 M next equal to null pointer. So when we did that, then this becomes grounded, or this becomes null pointer. So we built a linked list. All right. Now we can see that actually we can simplify our life a little bit in terms of the construction. What should we be doing? We can define, so if that had been a class, right? So if we have a class of SLL node, so in the public section of the class, we can define a constructor SLL node that can take in int a item, and along with that, it can take in SLL node star a next. So we are defining a non-default constructor inside. Okay, and let's just do the initializer list here. So we put a colon. And what are we initializing? We are initializing the member variables. So M item, and we are passing in a item. So this essentially is assigning a item to M item, comma separated, a M next, a next. And then there is nothing else inside the constructor. So we close that. Let's define one more default constructor. So which is just passing in a item. Here, what we want to do is that we want to initialize the M item with a item. And what should we be setting here to M next? Any thought?
Null pointer.
Exactly. So we will be setting this as a null pointer. And then there is nothing else to do here. And let's close this. And you can think that whatever I wrote above, that's what is there in the private section of this class, what I put in the struct above. All right. So
Wait, just to clarify one thing.
go ahead.
So when you initialize using that one colon there,
Mhm.
it's kind of the same thing as like if we were to put it in the curly brackets saying like M item equals A item, right?
Yeah, the advantage is that this gets executed before anything that comes here.
Oh, right. Okay.
So this is what is called the initializer list. Okay. All right. So now that we have defined these two non-default constructor, now I wanted to show you just by doing this, all these lines that we wrote here, you see how simple this now becomes. So now we were pointing 7 to 6, 6 to 3, and then 3 to null, right? This is what we are trying to construct. So what can we say here? So we can do SLL node star n1. Okay, so we are constructing this 7, right, which is n1. So we can say new SLL node. So now SLL node, you can see we can now take advantage of the non-default constructor, which takes in an item. But what is the next item that it is 7 is trying to point to? It is 6, right? So the first item is the item that it contains, which is 7, right? So therefore I pass 7 as the first argument. Then the next is going to be set to the next node, but we have not yet constructed, right? So comma followed by, we can construct new SLL node. And what are we constructing here? With 6. And what is the next pointer for 6? It is 3. So we can say new SLL node passing in 3. I can close it because you see here we are doing the null pointer assignment anyways. And then therefore I'm done. So a single line as opposed to writing so many lines. I just wanted to show you what is the power of non-default constructor here. Okay, now let's discuss. Any question? Okay. What are the advantages of lists over arrays? Any thought? I mean linked lists here. So advantages of linked lists over arrays. Remember we discussed 2 points there about the arrays.
Like you can point both to like the next node or like the back node. So if you want to add something, like you can just reassign the pointers instead of having to shift like an entire kind of list of, for example, numbers. Like you just have to reassign the pointer to some other node. Right?
Exactly. So as long as you have a pointer to the previous node, so that's a big condition here. So if you have a pointer to a previous node, inserting an item into the middle of linked list, middle of a linked list takes, how much time is it going to take? We are going to formally introduce the complexity theory later. So this is called constant time. Constant time means that it is not dependent on the length of the list anymore. So it's going to take constant time. And what is the second point?
You can make the size as you go. It's easier to change the size.
Very good. So the list now can keep growing until you run out of memory, until memory runs out. So effectively, this means that no need to resize the list. Okay. So having said that, now let's talk about how are we going to insert. So inserting a new item Okay. So suppose you are writing this inside the SLL node class. Okay. So somewhere in the public section, you're writing this, that insert after. So when I'm saying insert after, so this is going to be void. So insert after what? What do you think is after here? So we are inserting an item. So a item, we want to insert this, right? Let's say the value of this item is 6. Okay. So if I write such a function, what is this supposed to mean? Insert after what?
The current node.
Exactly. Remember the invisible parameter here? This node, right? So inserting a new item after this node. Okay. So let's see how are we going to write this. So let me just first illustrate how this would look like. So here you have, let's say 12, and this points to something 10, this points to 9, and you end. And suppose so this pointer is here. Remember, this is pointing to an instance of the SLL node, right? So you have many instances of the SLL node in this linked list. So suppose that this pointer happens to point here, and you want to insert a 6 here. So what is it that needs to happen here? Let's just change the color here just so that I can demonstrate. So we want to first allocate some memory for this guy, right? You want to allocate some memory with the M item initialized to 6, right? Right? So I want to construct this, right? It is a new node that you're constructing because you want to insert. And when you're creating a new node, remember the constructor that we have defined? When we are constructing a new node, what are the two things that are needed? I need item and I need a next pointer, right? Or I can just use the item, in which case the next pointer will point to null. So if you want to make it very sophisticated, right? So we can set everything in one go. So when we are constructing this new node, we populate because we have our non-default constructor. So I can immediately pass in 6. And as far as the next pointer is concerned, I want to point to this guy, right? Because I'm inserting after this pointer, which is pointing here. And I want this pointer to point to this guy. This is the effect I want to achieve as a part of the insertion process. Okay, so now let's see how we can achieve this with the help of the constructor that we had defined. So first thing that we have to do is we have to construct this node, right? So we can say new SLL node. What are we passing in? What is the first argument here? Can you tell me? We are constructing this node, okay? This has now been abused, but we want to construct a new node which is meant for this item equal to 6. What should be the first argument here? I'm now writing this function here.
6.
I'm writing this function right now, right? This is the inside.
Oh,
So what should be the first argument here?
A item.
Exactly. Right? A item is 6 here. What should be the second argument?
This.
You see where next should point to?
It shouldn't be this, the pointer. We're calling it the next, M next.
You see where M next for this. So we are constructing this node, right? So 6 is the first element, which is A item. What is the next pointer for this one supposed to be set to?
We need the M next within quote unquote this, right?
Yeah, because it's the M next with respect to this, right? This pointer's next is what this should be assigned, right? So essentially it is this, the M next of this, but we don't write this, right? Because it's implicit. So we just write M next here. Just by writing this, what I have done is that I have constructed this and also pointed to this guy. Only thing that is remaining right now is to assign this pointer's next to this guy, right? Correct? So therefore I can say M next equal to, right? Because this is the M next with respect to this originally. When I assign to this, then this gets set. In one line, my insertion is done. Isn't this elegant?
Yeah, and so when you put in M next in the second parameter,
Yes.
it would technically work if you also explicitly write this arrow M next, right?
Yeah, absolutely. But as I said, whenever you're writing any member variable, right? There is always this is involved there. It just, you are not needing to call that out. But the compiler is always seeing that in relation to the this pointer.
Yeah, I'm just like, for my notes, like I think it's clear if I make it clear that like this is there, you know. Like obviously I understand that it's always pointing invisibly, but just so that I know.
Yeah, and you can actually in your mind you can spell it out as this instance. You know, if even the this pointer is confusing, in your mind you can say to yourself it is a this instance essentially. So M next of what? Of this instance that I'm dealing with. Okay, so insertion is clear. It's just one line. Okay, so now what is the disadvantage of let's see. So what is the disadvantages of the data structures that we have written so far, the SLL node? Can you think of any disadvantages of linked list?
You always have to keep track of the next and the front. So if you lose one, then like you basically break the list, right?
Yeah, sure. And that is part of the node data structure, and you would have to maintain it because anything that we are allocating memory for it needs to have a valid content, and that is the responsibility of the programmer. And that's where the C++ language becomes a little complicated, because one has to take care of all the memory management. But I'm asking more fundamentally, if you again compare with the arrays, we identified what is the advantage of a linked list with respect to the arrays. What would be a disadvantage?
Traversing is more difficult.
Can you repeat that again?
Like traversing a linked list is a little bit more difficult than, say, an array.
Okay. In the case of arrays, you just index into an item, right? If you have to get an item. So here, finding, let's say, the nth item in the list takes time proportional to the length of the list. If you have a really long list, right? Suppose containing 500 items, right? And you want to find out what is the 499th element here, right? You do not have any indexing mechanism. So all you have to do is you start from the beginning of the list, whatever the head is pointing to, and then you keep walking all the way to 499 times, and then you get your item. But in the case of array, you just simply index, right? In the case of array, you just say 499 minus 1, and you get the value back. Is that clear? So you can see, if you want to summarize, there is a tension between inserting a new item versus finding a given item, right? In the case of arrays, inserting a new item is painful. In the case of linked lists, is very straightforward. But in the case of array, finding a given element, particularly when the index is known, is very straightforward, but here it's going to take a long time. Okay. Any question? All right, so now let's move on. So in general, so although I had been expressing in terms of the list of integer, in general, you can think of, if you want to generalize this, it will be a list of objects. So list of objects where you will have the item as a pointer to any object. So the item can be a pointer to any object. So you can have something like this, either a pointer, or it can be directly the object is there. So your structure will look like something like this. So SLL node, and then you will have, let's say, an abstract class called item, right? And you will have M item. Now, whether this is going to be a pointer or not, that's a consideration that one has to make all the time, based on whether it makes sense in terms of minimizing copies as well as the possibility of it being a null pointer. And then you have this is the reason why linked list is called the self-referential list, because you have pointer to itself, right? And that is M next. So this will be the most general sort of constituents of any linked list node. So what have we done so far? Have we really defined a linked list? What have we achieved so far? Have we really defined a linked list? The linked list class, I mean. We have defined a linked list node, right? Still, we do not have the linked list yet. Is it not true? So let's think about how we are going to have a SLL or singly linked list. Class. How do we arrive at that? Okay, there are two problems with just having SLL nodes. Can you think of what problem could be there if you just have the linked list node, but nothing having in relation to the linked list itself?
You don't have a pointer to the front, maybe?
Yeah. So if I am just building using different linked list nodes, and if anyone gets handle or a pointer to any of the nodes here, right, they can start manipulating the whole list. So if I do not have an encapsulation around the linked list node to produce a linked list class itself, it's very dangerous. So suppose I'm maintaining a shopping list, okay, using my linked list, and I'm adding to the list, I'm deleting from the list, whatever I need to do, and then somebody else is getting hold of a pointer and start thinking that, okay, this is the list that they need to manipulate. So I have set 4, 5, 6, and they happen to get into this element 5 by looking up through some other pointer, which we have somehow inadvertently given access to. So then the data can easily get corrupted. But there is a bigger problem than that. Bigger problem is that we have still not reached any resolution on how can we define an empty list. Because we just have a series of nodes and then we have just built a connection. How do you define an empty list?
Head pointer is to null.
Cannot hear you. Sorry. Can you speak louder?
The head pointer points to null.
Yeah, but there is no head pointers that we have defined so far. We have just conceptually spoken. SLL node doesn't have any head pointer.
But oh, that would be in
That would be what?
SLL.
Yes. So we have not yet gone there. So I'm just pointing out, if you just have a bunch of SLL node, there are two problems. One is that the data can easily get corrupted if somebody gets pointed to any node within your list, because it's kind of open, right? And secondly, the notion of head has not yet been formalized. All right, so I hope this is clear. So solution is having a separate SLL class, which encapsulates all these SLL node. And this guy is going to maintain the head pointer. Okay. Now, along with the head, we can also maintain other attributes in the SLL class if you want to. For example, we can track the size of the list. So anything pertaining to the overall list, we can start maintaining separate attribute. That's the advantage of encapsulation. So by bringing the size into the picture, this gives us an opportunity to maintain some invariant associated with the list. What is an invariant? That you would be able to prove something, that this list maintains certain properties. So for example, if you remove one element from the linked list, then you can say that the size must have reduced by 1. And you can draw out assertion on the basis of that. So this kind of encapsulation, so separate this encapsulation is essentially allowing you to define invariant associated with your class, the list class. So now with this, if you want to find out, is my list empty? Now it's very easy. All you have to say is that my size is equal to 0, right? Okay.
Wait, are there any like examples of invariants that are common other than size?
You can say that, let's say the list cannot be cyclic, for example, because you are controlling the growth of the linked list, right? So you can guarantee that the list cannot contain a cycle, for example. That makes sense?
Wait, how would that look like in terms of like,
So
how would you
when do you get a cycle? So I'm just going on, right? If suppose there is no encapsulation, I'm just all I'm doing is I'm just assigning some item value, and I'm pointing the next pointer to a valid node, right? So when there is no control through an encapsulated class, I can choose all of a sudden, or anybody can choose this to be pointing to this particular node, right? But if I'm the one who is implementing the list class, I will make sure that this situation does not happen. So therefore, it maintains the invariant that this list can never have a cycle. That makes sense?
Yeah, conceptually that makes sense. But like, I guess we'll learn later how we specifically implement that, right?
Yeah, so you can see, so right now, if you have to implement this SLL class, so in the private section, what are we going to introduce here? What would be the data member of this list?
So you'd have the head pointer,
What should be the
then
type?
the side of SSL node
So
or
SLL
pointer. Oh,
node,
sorry, SSL.
SLL node star M head, right? And that's all is needed to manage a list, right? And then you can add a few other properties, as I was mentioning. You can have int m size. Now, whose job is to maintain the the m size consistently? Whose job it is? Whoever owns this, right? Whoever. So now with the class, what we have done is that we have established a sort of ownership. Who maintains me, right? When you do not have a class, the variables do not have ownership, and because of which they go out of control, right? But because of this encapsulation, now they are being maintained by the SLL class. And therefore, no matter whatever method is written, it's the responsibility of those methods to maintain consistency of the values of its data members. That makes sense how the invariants are going to be maintained? So if I have in the public method, you have an insert item, right? And you pass in int a item, and whatever you may write, you have to make sure that both of these m head and m size, at the end of executing this function, they have a valid values, whatever the interpretation of this particular function is. So when we are inserting an item, what should happen as a result of insertion? The size must increase by 1. Whose responsibility is that? It is the responsibility of this member function, because every member function is responsible for leaving the member variables in a valid state. If it is not leaving the member variables in their valid state, then they're not written properly, or there are bugs in the member functions. So in this way, you are able to assure that there will be certain invariants which are going to be maintained. Does that answer your question? Is that clear?
Yeah, that makes sense. So then in the curly brackets, you'd be like m size plus equals 1 or whatever.
Yeah, here it should have definitely m size plus plus. Always remember this statement that I just made, that it is the responsibility of the member functions to maintain the validity of each and every data member. It cannot leave its data member in an obsolete state, because these member functions are instance specific. And instance specific means that they are associated with this pointer. Here is a this pointer, right? And this pointer meaning that they have now access to both of these data members, and therefore it has to take responsibility for maintaining the members that are accessible through this pointer. Okay. Now let me ask some fundamental questions. So why make things private? Why are we choosing these data members to always be private? So this is offering protection against corruption of the data. Because a private method or field, or we can say private member, is invisible and inaccessible to other classes. Now, apart from this protection is one reason why make things private. The second reason is that you can improve the implementation without causing other classes to fail. Because these members are not exposed to other classes. There are no other classes that can access those variables. Therefore, you can continue to improve your implementation without worrying about affecting other classes. Okay. Okay. Let me just take this opportunity to define the abstract data type. So interface. So every class you can think of has an interface and implementation. So typically an interface of a class is a prototype for the public member function and description of its behavior. An abstract data type also abbreviated as ADT is a class with a well-defined interface, but the implementation details are hidden. So implementation details are more linked with whatever the private members as well as private functions that this is dependent on. So only thing that any abstract data type is wanting to expose is a well-defined interface. And the interface is just a prototype of a public member function and a description of its behavior. Why I'm writing all of this is that the linked list class that we just introduced, this is now an ADT, abstract data type. And I'm just trying to bring out, because it's like you have introduced a new type that did not exist before. And as I said before, by keeping the implementation details hidden from other classes, now you can flexibly implement in different ways without necessarily whoever is dependent on the interface to worry about the implementation details. Like for example, you have written a particular way in which you are inserting an item into the linked list. So insert item could be a well-defined interface in the linked list abstract data type. But how you have implemented that is completely dependent on you. So whoever is using the list, they need not worry about how exactly you are implementing the insertion within the linked list. And this also brings us to the point of invariant. So invariant is a fact about a data structure that is always true. And as we gave an example in the case of linked list, a fact about the linked list is when you are adding an item, the size can only grow by 1. So now the question is that is every class an ADT? So there are classes which are not abstract data types. So sometimes the objective of a class is to only store data and nothing more than that. If you remember, when we defined class, we said that class is just a collection of items. So therefore, not all classes are ADTs. Okay, so when it is only storing data, then there is no invariant coming into the picture. Okay, so now let's return back to our SLL ADT. So what advantages that we are getting from this? That first is that it enforces invariance. And we already kind of mentioned that the two invariants that this guy is maintaining, which is that M size is always correct. And the second invariant that we just mentioned is that the list is never circularly linked. And we are able to achieve this goal because only SLL methods are allowed to change the list. And how did we ensure this? First is that the members are private. So which means that they are inaccessible to any other classes. And second, we can ensure by no method in the SLL should return a pointer to SLL node. Which means that you are not giving access to SLL node outside at all. So this now makes sure that there is no leaking going on. Any questions so far?
Okay. This is a question like regarding yeah, like ADT, like if we, for example, instead of keeping the members private, if we make it protected, like would that not make it an ADT?
No, protected is going to be fine because it is, you're just making it accessible for the derived classes. And we
Oh, right.
discussed
Okay.
that the derived classes are fundamentally the base classes first.
Mhm.
And therefore
Okay.
there is no discrepancy there. All right, now let's discuss doubly linked list. So DLL, let's call it in short. So what we found in the case of the singly linked list, right? That when we have to insert or delete an item in the front, that's generally easy. So let me demonstrate that. So in your class SLL node, okay, sorry, in your class SLL, okay, you have a public method where we are saying, by the way, let's write down the insert first. So insert at the front, right? So insert, let's say front, is going to be very similar to what we wrote before. Int a item. I can go ahead here just to. How should we insert an item based on what we discussed? We can do new SLL node. We are creating with a item, right? And the next is pointing to
M head.
M head, not yeah, M head, exactly. And then that gets assigned to M head. Single line. So this was your head pointer. And this was the other items. So you created a new node, whatever it is, let's say the value same kind of 6, right? You're inserting in the front. So therefore you want this next pointer to point to whatever was the head pointer. And you want the head pointer to point to this guy. So therefore inserting in the front is easy. Likewise, if I have to delete, so void delete front. So this doesn't have to take anything because it is just the head pointer, whatever the head pointer is. Now you tell me if I have to delete an item, what do I have to do? So head pointer, now we have a head pointer. So you have to delete this item, right? Whatever is pointed to by head. What needs to happen? So I need to delete this item, right? So what needs to happen?
You reassign head to this arrow and next.
Exactly. Exactly. So how do we assign it to the next? Let's write down. So we can say m head equal to whatever was the next of the head, right? So m head next. So notice that I'm using a function here, which you can think of. This guy should return m next, right? Am I
Wait,
done?
why couldn't you do, like, why do you have to use that function?
Remember,
Oh, because it's private.
nothing is going to be in the public domain. we initially, for demonstration purpose, I started with struct and I said, okay, let's make everything class. And we discussed why everything should be private. We don't want the list to be tampered. But are we done with deletion or anything is missing?
You have to delete the node, right? Because we allocated space. Or actually, do we? I don't know.
So now what is happening with
Because
this?
we did.
What is happening with this guy? What is the situation with this guy? This guy is still pointing here, right? Nobody's stopping it from pointing to this guy, right? It's only that this is no longer pointing to this. It's pointing to this. And whatever the value is, it's there. And it's just hanging somewhere, right? Wasting memory space. Therefore, this needs to be deleted. So how do we achieve this deletion?
You can make a temp pointer.
Exactly. So we have to say SLL node star temp is equal to m head, sorry, just m head. Correct? So after we have done that, now we can delete temp. But there is still something missing. Can someone point out? What else could be missing? Can you think of where we might get into trouble? Can you think of where just doing this could be troublesome? Anyone? Is this always going to work, this line? Could you think of
What
a
if it's,
yeah, go ahead.
what if it's an empty list?
Exactly. So m head can be potentially null pointer, correct? In the case of empty list. Very good. So therefore we need a check. If m head not equal to null pointer, and then we do the rest of the things. We're still missing something. Remember what I mentioned, it's the responsibility of the member functions to maintain the member variables. M head is just one of the member variables we have defined inside the SLL class, right? Inside the SLL class, What else is there apart from m head?
You need a decrease size.
M size. So M size at this point should have been M size plus plus. And here, if we are really successful in deleting, so this also needs to be inside this block of code where we do M size minus minus. Now the member functions have done their job properly. Okay.
Wait, could you clarify the SSL start temp equals m head and deleting temp? Like, why would you assign it to the head pointer? Because, like, don't you want to delete that first node?
Why would I assign this guy? Which line you have problem with? This line?
So after the if condition.
Okay. Why did I assign it to
So the
10?
first. No, why do you assign it to m head?
No, I didn't assign it to m head. I assigned it to temp, right?
Or yeah, why do you assign m head to temp?
Okay. So let's look at here. So after the first line, temp is pointing here, right?
Mhm.
What had happened if I had, so I have two options, either to delete before this line or after this line, right? Before doesn't make any sense, right? Because you would be immediately losing the content of the head pointer. But if you do it after, the head pointer has already updated. It's pointing to something else.
Oh, because so now you're not pointing to
We have updated the
that first. Oh, right. Okay.
Okay. All right. Okay, now let's talk about, so what we established here is essentially this point, that inserting or deleting an item in the front, okay, let's be very clear, front of a singly linked list is easy. That's what we established here. Very, very easy. Now, what if I ask you, can you insert or delete at the end of the list? Is it still easy? What is the problem to delete at the end of the list?
You need to get to the end of the list first.
Exactly. So therefore, this is going to take time proportional to the size of the list. And remember, the list can be really, really long depending on the application. If you have 1 million entries in the list, and just for inserting or deleting at the end of the list, if you have to just walk down 1 million items, that's a lot. So what can we do here? So this is where doubly linked list comes in. So what do we have in the doubly linked list? So class DLL node. So singly is going in one direction, right? So let me just make a small. So this is your singly linked list, right? When it's a doubly linked list, it's also going in another direction. So you will have not only the next pointer, you will also have the previous pointer. And the previous pointer, and this points to null. So you have the head pointer pointing here. So this is your head. So naturally, a doubly linked list also need to have a tail, right? So this is the essence of doubly linked list. So now if you have a tail pointer, how long is it going to take for you to insert or delete at the end of the list? It's constant time, because it is not dependent on the length of the list. List can be 1 million items or 100 items. It's going to take the same time, because you have the pointer to the tail and you can insert there. All right, so now, so object, sorry, not object.
Sorry, Professor, just to interrupt. This is not necessarily relevant, but in this case, you're not quite doubling the size of the data, right? Or the amount of data you're using.
You
Because you're
are,
adding a bunch of addresses.
you are not doubling, but you are definitely, for every node, you are maintaining one additional pointer, right?
Right.
So there is an overhead that you have, and the overhead is essentially depending on the amount of memory it takes to store a pointer. So typically it can be 4 bytes or 8 bytes, depending on the machine. So you have increased 8 bytes multiplied by 1 million, right? If you have 1 million nodes. So that's a very good point. So there is an overhead, which is a space overhead, but what you're gaining is the time. So oftentimes the space and time, they are trade-off points. So when you try to improve the point, you have to sometimes sacrifice space. And when you don't want to sacrifice space, then you'd lose time. So this is a typical kind of, you can think of dynamic. When you are choosing a particular data structure, what do you want to worry about most? Is the space of a bigger concern or time of a bigger concern? And depending on that, you would choose appropriate data structure. So that was a very good point. All right, so now, yeah, any other question?
From your like industry experience, which would you say is like more value, like space or time?
If you are targeting low cost embedded devices, right? Typically space is a big constraint. And if you are shooting for high performing platforms with very, very powerful machine, there you can choose to dedicate as much amount of space as possible, but get the highest possible performance out. So it totally depends on the application.
Okay, thank you.
I mean, these days, when it comes to machines, you have very, very high-end machines with like GPUs, which contain a lot of processing elements inside. And when you are trying to map to GPU, obviously the application has a very, very high demand for performance. And they don't care about so much of memory. Okay. So here you'll have item. Let's put it as item type. I'm just trying to make it as generic as possible, because this could be of any type. And then you have DLL node star M next. And in addition to that, you now have DLL node of, you will have M previous. And in your class DLL, you will likewise have DLL node star M head, and you will have DLL node star M tail. And now every method that is inside the DLL class, inside the DLL node class, they have to manage all of these members. they cannot just choose to maintain only 2 of them. That will make the program crash. So they have to think about how to leave every single data member in its valid state. And always remember this point. Any question so far? So
really quick, just to be clear, these are separate classes, right? Not one with another.
good point. So one may choose to actually make it even this guy inside the DLL, so that it assures that nobody even has access to this. So it makes this also private. And you will see in some of the implementation files that I would be sharing with you, it will have sometimes this kind of implementation. Very good question. By the way, when we put this inside, right, this kind of way of composing the class, generally when we use the word subclass, right, we generally mean that we are deriving in a hierarchy. This is not called subclassing. This is just composition. Okay. So what we have achieved with the doubly linked list is that now insert and delete operation. So delete items at both ends in constant running time. All right. Now let's look for one more elegant DLL. So we saw that right now we have at least 2 items in the DLL, and which is the M head and M tail pointers. And so the question is, are we able to manage the same without necessarily paying a cost for both M head and M tail? Okay. So let's introduce a new node called Sentinel. So this is a special node that does not represent an item. Okay. So let me show you how we are able to introduce a new circularly linked list, which is achieving the same behavior with elegance. So let's call it CDLL. Write down properly. So this is CDLL. It's a circularly and doubly linked list. So here, what we want to have is that M head is the Sentinel node, which does not store an item. So it would look like this. Class CDLL, and we can say DLL node star M head. So this is our Sentinel node, and you can have still your invariant being maintained. So how is this going to look like? So if you have a linked list, a doubly linked list, okay, and you have a special node which we are calling as the Sentinel node, which is being pointed to by the M head, right? So this Sentinel node will have is previous pointer pointing to the first element, and the last one the next pointer. So this is your next pointer and the previous pointer. So the next one is going to point to the previous, point to the first entry in the linked list. So with that, what we have achieved is, let's say, let me not mess up the color convention. So let's draw all the previous. And the next for this guy is going to point to this. There is something wrong. The next one of this one is pointing to this. The next one is going to point to this. And just see if I can erase this. Previous one has to point to this guy. And the next pointer the next of this one is going to point to this guy. And the previous is looking like a little messy. Okay. So here I'm trying to show how, with the help of just one node, we are able to combine the effect of the head and tail pointer together. Because when you are asking the Sentinel node, what is your next? So M head's next is going to point to the first element, and M head's previous is going to point to the last element. So this would be an elegant way of just saving some memory. So this is the first element, and this is the last element. Is this getting clear? Remember the problem that we were trying to solve using the doubly linked list is that we want to be able to very easily insert as well as delete the first and the last item. And therefore, the challenge was that how quickly can we get to the first and the last element? So we were maintaining both head and the tail pointer. So here, by introducing a dummy, so here the value is irrelevant here. By introducing a dummy pointer, which we are calling as a head pointer, which represents the sentinel node, we are able to very easily get to the first as well as the last element. So this is a circularly doubly linked list, which just helped us optimize some space. So we are just able to have only one pointer and yet able to achieve the goodness of the doubly linked list. Anyways, I just wanted to show that how you can drop
So
one.
if you were to like initialize the, or not initialize, but the doubly linked list, so you'd, or I guess you would initialize, so the values in the sentinel first, or like M head would always point to the sentinel.
Yes.
So in order to access the first node, you have to kind of dereference the, so it would be the next
pointer. And if you want to access the last, it's going to be the previous. This is the previous.
Okay.
It just, I'm just showing you, like, if you want to optimize and make it a little more elegant, this is how it would look like. It's not such a big saving in one sense, because if you have only one linked list, you're still maintaining the next and the previous pointers, right? For every single node. But this implementation looks a little more elegant than maintaining two pointers, M head and M tail. That's the only advantage, I would say. Actually, in terms of saving also, you can think of not much we have gained in one sense, because for this dummy node, you are dedicating for previous and the next pointer as well. So it just, you can appreciate the elegance of this data structure. That's all. I just wanted to show you how alternatively one can make a doubly linked list. Now, what would be the way to check whether this is empty? What would be the way to check that this is empty? This is going to point to itself, right? And this is going to point to itself. This is empty condition. So the priv and next field points to itself. So empty when prev and next point to itself. All right, I hope you're able to appreciate to some extent this data structure. Otherwise, I think pretty much that's all I wanted to cover for tonight. We can move on to tonight's lab assignment. Just before I move on, I just want to ask one more time, do you have any questions or anything that was not clear in today's presentation? Any question? Okay. So if not, I would like to hand over to Matt for introducing the lab assignment for tonight.
Sure. One thing